This is CPE 133. This is Chapter 7 in the Free Range Verilog Foundation Modeling text, and this is Part B. So Part A went through a bunch of support work, which is kind of busy work. It's easy to fly through. What really matters is if you actually do some example problems. So we're going to skip through this really fast and get to the example problem that where we quit last time. And here we are. Let me fix my pointer here. And we are ready to go. Okay, so this is essentially write a Verilog model that describes this function here. As a function is defined with a table. So, tables, one of the first things you saw in digital design. That's how we defined our gates essentially, initially. But, we can define anything with a table. Not anything, but quite a few things are nicely definable by table, especially when you have a whole bunch of functions. Now, the nice part about this is we are using behavioral modeling. Now, Verilog supports tables very, very nicely. Now, the other option would be to use continuous assignment statements, which would be something like assign f equals a bunch of logic here. And I just don't want to do that. I could do it, but it's a giant pain in the arse. That's something we want to get away from. It's just kind of represents low-level modeling. We don't want to go there. So let's do this. And I hate to say it, but what I'm going to do is plop the solution out there and describe some of the pertinent parts of the solution. Now, the issue here is that it's a function, and so this function f here has outputs that are either 0 or 1. So we have a choice. We tell the function where the ones are, or we tell the functions where the zeros are. For this particular function, there's less 1, so we're going to describe where the ones are. So once again, the very first example, you get into the notion of there's just it's literally an infinite number of ways to model these functions or model these tables. It's just really powerful. I'm going to show you a couple ways. Hopefully you get a feel for it and then kind of develop your own style on these things. So once again, we are going to be defining in the circuit where the ones live. Okay, so this circuit here has 3 inputs and 1 output. The 3 inputs are A, B, and C, and the output is F. Now, once again, we're not going to use logic here. We're going to use this always block to do a bulk of the work here. We're assigning F inside the always block. Because of that, we have to declare the output F as a reg type. That's the only way we can do that to get it to be assigned in the always block. Now, once again, there's a whole bunch of different ways to do this. Quite frankly, one way is to take those 3 input signals and create a bundle out of them. Now, there's no reason I have to do this. It just makes the solution cleaner. And so I'm always gonna try that. I mean, it's not going to cause the synthesizer to synthesize more hardware. It's just going to make the solution cleaner. So here's my definition of a wire. What I'm going to do is take that wire and use a continuous assignment statement and concatenate those 3 signals together and call it essentially a different name, which is ABC here. Okay, so I'm ready to do this thing. And so here's my always block. Here's my always block. Here's my sensitivity list. What I'm going to do is put all the inputs, list all the inputs in that sensitivity list. So when one of those inputs change, it's going to, we'll say, cause this always block to be evaluated. Here's the begin and the end right here. I happen to be using a if statement for this one. The next solution will have a case statement. So what I'm saying is if the input values equals 0, 0, 1, the output is a 1. And we're going to back up on that one. 0, 0, 1, 0, 0, 0, 1, the output is a 1. So I'm actually, with that first if clause, I'm implementing this line in the truth table. Okay, so what I have to do here is implement, find those cases where the ones live, which I explicitly say here, and then for everything else, the output's going to be a 0. So this is the catch-all else right there, and essentially what I'm saying is that I'm listing explicitly the 3 cases that are 1, and then I'm using the catch-all to list the cases where the output's a 0. And once again, this is combinatorial function, which is why it has this catch-all else in it. So alternative solution would be to use a case statement. Works really nicely with the case statement as well. There's actually other formats you can use for this case statement, but this is the easiest one. So the case statement here, essentially most of the stuff here is the same as the previous example. The always block is the same. What we have here inside this case statement is, inside this always block, between the begin and the end is a case statement. Now, quite frankly, I didn't need to put a begin and the end in here since I only have one statement in there. But that's, it looks better with the begin and the end. It's more clear. So these are the 3 cases. It's the 1, 6, and 7 case, and if you look back on this one, it's the 1, 6, and 7 case, which have the 1 variables. Okay, so each of those cases here, what I'm going to do is assign a 1, and then I'm going to those specific cases, and every other case is going to be assigned a 0, which I'm going to do via the default, which is the catch-all for a case statement. Now notice this one, I could have assigned these as 1 and 0, but actually used official binary format, which is 1 tick B0. These values here could have been just as easily described as 1, 6, and 7 in decimal, but I opted to use a binary format as well. It's up to you how you want to do that. But anyway, those are our 2 solutions for this example. So moving on here. So we got this, huge example. I mean, it's kind of scary. Essentially, this is a 4-input function, A, B, C, and D, and it has 3 separate outputs. The T1, T2, and T3 are all functions of the A, B, and C, D inputs. And so looking at this thing, I'm going to try to look for ways to implement this very quickly. And what I'm going to see here is that for inputs 9 through 15, the outputs are always equal to 0. And so I'm going to leverage that, and it's going to make my code a little bit shorter in the solution here. So let's go look at these solutions. So first of all, I should have done this in the other one. Black box diagram has 4 inputs, A, B, and C, D, and it has 3 outputs, which is just T1, 2, and 3. This one just so happens to be declared as bundles, so I don't have to concatenate them together, which is just to save space. This particular solution is implemented with an if-else statement. Here we go. These are the cases 1 through 8, where typically speaking, these cases here, all are 1 cases 1 through 8, have different values to them. Those values are reflected right here, not that last one. So essentially what I'm doing is taking this table here, changing it around such that it matches my if-else format, and that's it. Now here's the else, which is the catch-all, which represents 9 through 16. Since all those outputs are 0 in there, I can assign them a 0. But keep in mind, this 110 here is equal to this 110 here, because this is the 0 input. Okay, and now these are actually specified as decimal, which was just a choice. I could have put anything, could have put hex or binary, blah blah blah. This one just so happened to be hexadecimal. Keep in mind I did use the equality operator there. That's not an assignment operator, and that's all I can think about with this example. So I think we're going to see this example again with a case statement. Here it is with the case statement. Everything's bundled nicely. These this essentially, once again, it's essentially this table put into a Verilog format. So these are the first eight variables up here. This catch-all, which is the default, represents these essentially inputs 9 through 15. So I happen to put, just so I happened, arbitrarily put the item selectors in decimal. I could have put them in binary as I did in the other examples, and I'm thinking that's all I can figure out in this example. It's, once again, it's a table, it's a lookup table, it's a combinatorial circuit, which is why I implemented, which is why I have a default in use in there. So this is a similar example, and it's what I'm trying to do with this example is, show you how you can use these if statements. It's very super flexible. Now this issue is it's the same function, but I'm going to put essentially a chip enable on it. Now the chip enable, essentially, when it's asserted, it's active high, it implements this table. When the chip enable with CE is low, the output's all zeros. And so it's going to be very straightforward to do this in this code here. So here I am, here's my CE, here it is, my chip enable is an input here. This essentially is the code from the last example, but what I'm doing is wrapping this code up inside of an if statement. So here's your if CE equals 1, that means the chip enable is asserted, then it acts like the normal decoder that we used in the previous problems. Okay, if the chip enable is 0, that's going to be covered by this else, which is catch-all according to the problem specifications. When the CE is not asserted, what I'm going to do with the output is make it all 0. So essentially this is the CE active high case, this is the chip enable or CE not asserted or disabled case. Once again, a whole bunch of different ways to do this. Keep in mind that this if statement here, I didn't use begin and ends on it because I only have one statement inside the if, which is the case statement, and then I have only one assignment inside the else, which is just simple assignment statement right here. And I think that's all I can think about on this problem. So in general, we've been using, in our examples here, we've been using both wires and wedges. So this is going to be a really important subject as we go on here. It's actually very simple the way we're going to do it. Essentially, when we assign something from an always block, it has to be a reg. So keep in mind, so within an always block, the right side of the assignment operator, it can be a wire or a reg, but it's the left side of the assignment operator in the always block that has to be a reg type. And essentially, once again, the module input for the external interface can also be a reg type. We saw that in a couple examples here. So when I'm assigning something from outside of an always block, the right side of the assignment operator, which is an assign statement, a continuous assignment statement now, can be a wire or a reg type, but the left side, in this case, needs to be a wire. So in summary, we were working with behavioral models here. The heart of the behavioral models always block. A couple different ways to assign stuff in always block, just straight assignment, but also we have procedural programming statements, which are the case and if else statements. Inside those case and if else statements, and then just inside the always block in general, we have two types of operators, of assignment operators, which is blocking and non-blocking. The examples we use were decoders, which are combinatorial circuits. When you're working with combinatorial circuits, you always use blocking operators. When we work with sequential circuits later, we'll start using non-blocking operators. Bunch of different operations in Verilog that you need to be familiar with. One is concatenation, super handy, which we can use these curly braces here. We also can represent integers in various formats. formats, which is hexadecimal and binary. We typically never use octal. A whole bunch of different equality operators in Verilog. What we see here is 2 of them, and we'll be getting into more as we go on later.